Thanks. Wait, as the last speaker, I am obliged to ask, well, I guess I'm not obliged, but I want to invite us to thank the organizers for a great conference and a fabulous ice storm. Thanks, Montreal. No, really, it's been super fun. Okay, so what is my plan for this lecture? Last time we proved modularity kind of rushed at the end that if I take any, say, closed manifold, and I take any map, any homomorphism in the group of homeomorphisms of M, or even just the identity component to another reasonable, separable, topological group. Any such map is continuous, which says that the homomorphisms in this group to other groups are quite special. You might ask, like, what are some examples? And it's kind of hard to produce really weird examples, but it's easy to produce some examples if you use the manifold M. So, examples, maybe I know at least one group kind of got to hear it in the problem session of like, what are some examples that you can make for various G? If I build G out of M, or out of homeomorphisms of M or something, we're in luck. So for instance, here's some, like there's a reasonable action of homeo of M on I don't know, M times anything. So I can say this is homeo of M, I don't know, cross S1 or something. Take another manifold, and then you can use kind of this like dumb product action where like you just have these copies of slices of M and you do act on them as you would, and you don't care about the other. That's not very interesting. There wasn't anything very special about S1 there. This could have been some other manifold. You could also, because I'm going to move to other homeomorphism groups, I'm going to write this as acts on M cross N by homeomorphisms. Right. You also have an action on, say, the configuration space of K points in your manifold. So this denotes the configuration space of K unlabeled points. But you could also like label your points, right? And that's just like a product of copies of M minus, say, a fat diagonal if you wanted these to be K distinct points. And this one is the quotient of that space by the symmetric group, right? For you, I forget the labels. But of course, you can see this action. You have a manifold. You put K points on that, and you don't label them. You just have some dots as a set. And then a homeomorphism takes this to another set of K distinct points. So that's a nice topological space with an action of this group on it by homeomorphisms. You can do something that's like a little more clever than just a product. Homeo of, say, the sphere acts on the n-dimensional ball by kind of coning things off. I take product of sphere times an interval, as I was doing this before, and then I just like actify one of the sphere sides, right? So I kind of put it off here. I have all these concentric spheres and I'm getting smaller. And there's a point at the center where I'm this. Okay, so somehow these are all built out of things at least as complicated as my original manifold. The question, which I'm going to slightly misattribute to Gis, she's asked it in the context of diffeomorphisms, but it's because it was at the end of a paper where he proved some things about groups of diffeomorphisms, and so that was the right phrasing. But it applies equally well to homeomorphisms. If the group of homeomorphisms of some manifold acts on some other manifold by homeomorphisms, okay, is the dimension of n at least as big as the dimension of n. So first way of asking, like, is this, as all of the examples I can come up with indicate, is this just some kind of more complicated space. This was answered by Sebastian Furtado for the diffeomorphism case in 2014 positively, but his proof is inherently like diffeo based, using things like Montgomery's event and these subgroups of diffeomorphism groups. And so it was just totally open whether this would work without all that smooth structure. There's another example. I wanted to mention one more family of examples. Sometimes the group of homeomorphisms of a manifold, but not always, sometimes you can lift it to the covers of a manifold. For instance, if I took, say, a genus 2 surface, a hyperbolic structure, there's an action of this group on the universal cover of the surface. Every isotopically trivial homeomorphism, that's what this means, it makes a unique lift to the hyperbolic space that's isotopically identity, or that fixes the compactified boundary point lines. And that defines your whole group theoretic lift of this group in action on this space. So there's nothing special about a 2 here. This was just sort of to a hyperbolic surface. But if you try and do this, like, I don't know, homeomorphism group of the circle does not act on the line, its universal cover, because you have coordinate, you have an arbitrary finite order elements acting on the circle. There's no finite order orientation preserved in homeomorphism of the line. So somehow this is it's already an interesting question to ask, like, when do you have this? Okay, so I'm going to as much as I can a theorem that answers this question. And then with more work, you can do more with it. This is due to myself and Lei Chen, and something we did a few years ago, but has yet to appear in print, so I don't know how to date these theorems. Sitting in some journal with a long backlog. But the statement is as follows: suppose that you have an action of the group of homeomorphisms of a manifold, identity component, on some other manifold. So I guess we need some like finite dimensional stability context. And it's a manifold for today. In some strong way, they resemble all of these examples, and it's built from pieces that look like things I just gave examples of. So then each orbit action. So what does that mean? I take a point in N and I look at its orbit where it goes under this action. Is the image of some cover of some configuration space of points in M. Image under what? Under that continuous injective. So another way to say this is that orbits of this action are like locally injective copies of just covers and configurations.
Can I say more than continuous and injective?
No, they might like come around and accumulate on each other or something like this. Yeah. Imagine that action, well, actually it's hard for me in one sentence to give a non-trivial example, but some people were listening to me in 20 minutes ago in the break to do ones where they really accumulated all over each. I have time on the limits. But they're locally embedded concepts. Okay. This theorem immediately answers the question of G's, right? If my action is not trivial, I should say, I guess this action is not supposed to be the trivial action when you don't move anything at all, then there's some orbit that is not just a globally fixed point. So that says that I have to be cover of a configuration space of more than 0 points in a manifold. And so I'm at least at const of 1 covered. So my dimension is at least the size of M, and that gets locally embedded. So here's the answer. Another consequence of this is actually we're able to classify all actions of homeomorphisms of spheres on balls. As soon as your ball has dimension at least 3, here's a rigidity theorem, everything is conjugate to this coning off thing I already gave. If your dimension's 2, you may notice that what is that? Then that becomes the one-dimensional circle. Configuration space of 2 points in the circle is, oops, that's a Mobius land. But if I take its cover, 2 labeled points, that's an annulus, and I can stick some like annuli inside of this to make an example that's not this. But that's an accident of low dimension, and they all end up. So that tangential remark is to give you a sense that this theorem has various consequences where you can start classifying these actions. Now that you know what the orbits look like. So, but there's still like a giant next problem, a whole family of problems. We say only a little bit about, and that's to classify, you know, all actions of some given M on some given N, on a given Homeo of M on a given N, you know, by understanding how orbits move together.
So when you say classify up to
Conjugacy, right? So I said without writing down, here's a theorem up to conjugacy, any action of Homeo of S 2 or 3 or 4, anything bigger than 2 on a 3-dimensional ball is this coning off picture of conjugacy.
Conjugacy or
Conjugacy.
I wouldn't fix a certain form.
No. You have a single fixed point, and yes, this is all that you have a bunch of concentric spheres, and you're all doing what you would normally do as homeomorphisms. You rotate them in particular. And you should also believe you don't have some kind of open set of fixed points, because you're going to have finite order homeomorphisms in your sphere. And a finite order thing shouldn't fix an open set. Yes. Yeah, I mean, that's not obvious. I think that was a surprise. I actually didn't believe that was true until I proved it. So, okay, but what I want to do is, so this is just to say that there's a lot of rich math to be done, but what I want to do is prove this theorem or give you an outline of proof for some steps. Like set it up to make at least some of the steps feel familiar, like things that you've seen before. Okay. Okay, so to prove this, I won't get to the ugly parts, but that's great. No one wants to see that at the end of our conference anyway. I'm going to start with a definition. All right. This is just a definition for any topological group. So let's say D is some kind of topological group. We'll see why this is a useful concept in a moment. I'm going to say that just a subgroup, so A is just a subgroup, is something that has quote unquote codimension less than n. Okay. There's no precise word, the reason I'm calling this codimension, except that it feels like codimension means if, here's the definition, there does not exist a topological embedding of a n-dimensional disk into G that survives the quotient to G mod A. So this doesn't have to be, doesn't have to be a subgroup, it doesn't have to be anything. This is some kind of like topology-ish statement. So what this hook arrow means is that this thing is it descends injectively to the quotient. It has to remain an embedding, but if it doesn't run into itself very much, you could shrink to a smaller one and it should remain embedded. Okay. Good. you know, so why codimension n, right? This is supposed to say that like G mod A, whatever it is, looks like a thing that's dimension less than n because you can't fit an n bits inside there. Okay, here's the key proposition that is gonna quickly bias the theorem. So let me state the key proposition. So it is about codimension, small codimension subgroups, finite codimension subgroups. Suppose I have inside of a group of homeomorphisms of a manifold, a closed subgroup that's a codimension at most n. Okay. Then what can I say? Now I can say something about what this looks like. It's going to look like a stabilizer of a small number of points. Right? And somehow being able to move these points, being able to move points around independently or something is going to give me codimension. So more precisely, then there exists a finite set, you know, of points in your manifold of cardinality less than n, so that A is contained in the stabilizer of this. So this stabilizer is just like the set of homeomorphisms that map this set to itself. I'm allowed to permute the points. That's fine. And inside of A is the subset of this that that does not permute points or even braid them at all. The identity component of the stabilizer of X. So I've been using this for identity component of the group, so I'll do that again. You should parse this as saying that, you know, small codimension subgroups look like stabilizers of sets. Okay. Well,
That's the set-wise stabilizer.
yeah, set-wise stabilizer. Yeah. This is contained in the pointwise stabilizer, of course, but I'm probably smaller. Right, if you imagine you have points and you like isotope them around your surface in some weird way and move them back to where they are, there's no way to always stabilize those points and get exactly that homeomorphism, right? You imagine like point pushing subgroups or something, they're not in here. This is something much smaller. Okay. Let's prove my theorem given this proposition, and then we're going to prove the key proposition or do as many little steps as we can.
What does it say for n equal to 1?
What does it say for n equal to 1? Oh, if I let's see. I might need so let's see, codimension less than 1 means that I can't embed interval into here, and A is a closed subgroup, so I should probably do the whole thing, I guess, is what's going to happen. Yeah. Here it is a necessary hypothesis for this thing. Yeah, that's where closed came from. And that's, I think, is where it's going to get used. There's an epsilon chance that there should be some less than or equals instead of less than, but I think I have this right. Okay. We'll see in the proof of it. So here's proof of theorem given the key proposition. Okay. So suppose the homeomorphisms of your manifold acts on some other manifold. And I want to understand orbits. So Y is a point in F. So let's look at not the orbit, but sort of the opposite, the stabilizer of Y under this action. So let, I don't know, A sub Y be the set of F and Homeo, such that maybe I need a name for this action. So I'll denote it as it's a homomorphism, maybe phi, like before, from Homeo not of n to Homeo of n. So phi f of y equals y. Okay, automatic continuity says this action is continuous. So this is a closed subgroup. And
You need, how do we know that the target group is separate?
Homeomorphism groups of manifolds are separable with their compact open topology, blah, blah, blah. Maybe you can believe you can piecewise linear approximate things or something like this to get some dense set. Okay, so there's a closed subgroup. And if I look at the quotient, or just the cosets of this, this maps nicely into M, right? And it gives me the orbit, right? Left coset of AY mapping to F of Y is, sorry, phi F of Y. That's a well-defined, this is a continuous injective map onto the orbit of Y under this action. Okay, so let's see. Good. So now what am I left to say? I want to say that this thing looks like some cover of some configuration space, because that's what the theorem is telling me. Okay, do I have this? Well, let's use my proposition. So my proposition, there exists some set X, which depends on this little y, right? Some finite set, such that, well, what I just wrote there, right? Stabilizer of X identity component is contained in AY, is contained in, these are possibly equal to stabilizer of X. So that means that if I think about instead the sequence of quotient spaces, this is the bigger one, this will be the bigger space, but I have maps. Sorry, Homeo. And I should have given that a name, not Homeo N, not AY. And Homeo mod smaller group. I have these surjective maps called mod out by successively bigger things. This composition here is a covering map. Okay, so I want you to believe this, and I'm not going to do all the details because it's actually a slightly annoying thing to say that, like, the set-wise stabilizer of a point and its identity component behaves nice. But if you think of, like, I don't know, Lie groups, and you looked at the identity component of a nice topological group, right? Then quotienting out by some space by the identity component gives you a covering map in this sense. The fibers of this are going to be discrete. Okay, so what does this say? This says that this thing is some intermediate cover. And what is a homeomorphism group of a manifold modulo setwise stabilizer? That is just the configuration space of X in M. This one is the configuration space of X in M. We did a baby case of that where I was talking about, like, the configuration space of Y or something almost. Well, not quite. That was a stabilizer. Oh, I was writing these as sets of sides. So maybe I should say this is the configuration space of number of points in X in M. Topologically, these will all be the same when X has whatever size. Okay, so the theorem is really the proposition, right? This is just unpacking it into the language of what do we have to prove. Now it's something about small codimension subgroups.
Right,
yes.
You can apply the proposition exactly because you look mapping off this orbit and Y. So you get some stuff about codimensions. Is that
oh yeah, right. So I should say that why is this small codimension? You inject into here, right? And so, right, by invariance of domain, if I could put a disk in here of larger dimension than n, then I would move that injectively into n, and that would break invariance of domain. Yes, thanks for, that was the missing part I forgot to write, right? So this has AY has codimension less than dimension n+1. Yeah, I think that's him. Okay. Okay, so now I have to prove this proposition, which is this abstract thing about, you know, small codimension subgroups and homeomorphism groups. So there's two claims, and we'll see how much I can prove on either one of them. Here's all the big white stuff. Okay. So let's see. Suppose A has codimension less than n. And somehow I have to find this set X that I'm gonna pull out of just whatever this map A, this A is. Okay, the first claim, okay, which I will defer the proof of because this is where you have to sweat a little, and it's kind of annoying, and we did some similar things yesterday. The first claim is that there exists some ball E embedded in your manifold, a little ball, okay, so that A contains all homeomorphisms with support on this little ball beam. And certainly that would be true if A was like contained a stabilizer of a finite set, right? Takes a ball that doesn't have a finite set at all, it better contain that. The first step is to show that. And the reason you should maybe believe that is, you know, here's a big proof, which is suppose not, right? Take n+1 disjoint balls, and you know, if each one of these contains some homeomorphism not in A, then I have n+1 independent things I can do that all survive the quotient by modding out by A, right? So if here's B1 up to Bn+1, if there exists some, I don't know, Fi supported on Bi not in A, then well, I don't know what to do, right? What I would really hope, and this is why this is a fake proof, is if there was like a whole one parameter family supported on Bi and this whole thing was not in A, right? Then we would have map, you know, topologically from a product of n-1 one parameter families, that's an Rn+1, into my homeomorphism group that survives its quotient by A, because like none of these were in A. Okay, well, even though it was kind of a lie, because even if each one of these individually is not in A, what if the product of some of them were in A? Things like that. Okay, that's where you have to work. This is the but this is the philosophy, is to make this idea push through. Being very careful, and this is where facts like simplicity of homeomorphisms stays supported on balls. This is where A being closed comes into the picture. I will say more words about this at the end if I have time, but I suspect time will not be on this. But hopefully this claim is at least like optimistically believable. There are tiny balls all over your manifold. Like it would be really hard to avoid all of them. So that's claim 1 and a fake proof. Claim 2 will be the real proof of. In some sense, it's more interesting because it tells you how to find X. I will erase my here. We reduced it to this. All right. Here's place view. Suppose, again with my setup I have, suppose I could find a bunch of distinct points that were in different orbits, different pairs. So let me take maybe I have x1 up to xk, and I have y1 up to yk, all distinct. The reason I named some x and some y, and it's the following. We're going to suppose that for all I, there is no homeomorphism in my small four-dimension subgroup A that takes xi to yi. If this is the case, then conclusion K is less than or equal to less than 10. What do I have to do this? Let me prove claim 2 and then immediately get out of claim 1 plus claim 2 that's going to be. And what's X going to be in the end? It's going to be like a maximal size set of these. Right? Somehow set-wise stabilizer, the points that set, I act transitively outside of my set X. And within X, so I can go, no, maybe I even fix all these points, whatever, but I don't move them outside itself. You should think of X as being like, I don't know, maybe all the X's or something like this. And then Y is all being points kind of outside of this. Right? I cannot move a point that in this set I've stabilized to anyone outside. It's going to pick it up.
Is it one function then, or is there a different function?
For each I, there's nothing inside of A that moves the I points X to I point I. Yeah. Wait. Is that this F? I mean, there does not exist an F in A, so that F of X. Oh yeah, sure. I didn't have to label it.
For each I,
there is no F. Yeah, sorry. Yeah. All right. Proving claim 2. I'm gonna, and here the picture is slightly different. If your manifold is like one-dimensional, I'm gonna draw the 2 and up picture. So here we go. I have my like x1 and my y1 and my x2 and my y2, etc. And I'm going to join these. If I have dimension at least 2, I can find disjoint arcs that connect. Go all the way up to k. And I can take tiny cards of my disjoint arcs that look like disjoint balls. All disjoint. And let's see, for each I, let Fi, I don't know what T, be a one parameter subgroup supported in this ball. So there's B1, B2, these are all disjoint, so these guys will commute with each other. This is like an R subgroup. And I want Fi at time 1 to take Xi for yi. So this induces, I have k commuting actions of R. I get induced action of R K on my manifold M. I get an RK subgroup of Homeo M. Okay. And what is this, right? I take T1 Tk goes to the composition of F1 to the T1 composed with Fk to the. And what's special about this action, I've made it so, let me draw a picture of RK here. I've made it so that if any of these Tj coordinates is 1, then you're not in A, right? Because if any one of these is like the time 1 map, it's taking Xi to Yi. So these green subsets of my RK subgroup of Homeo of M are not in A. Okay, and A is a closed subgroup, so A intersects this RK subgroup set is some closed subgroup of RK, and it avoids lines in each coordinate directions, while it avoids hyperplanes in each coordinate direction. So it must be discrete. you know, it'll contain the origin, but like, I don't know, maybe it's something like minus or this like. Could just be discrete. But that's fine, discrete is good enough, right? That says that there's like some disk subgroup that will survive this RK that will survive the quotient to A. This implies there exists some disk, not a subgroup, but a topological subset, right, inside of RK, which sits inside of Homeo. Okay, that survives the quotient, the space of cosets of A.
Why is there intersection discrete?
Why is this thing discrete? Yeah, so I avoid a hyperplane in each direction, and I'm a closed subgroup. This is some closed subset of this now as a topological group. So if I'm not discrete, I can paint a line, which is that I cut off hyperplanes in all directions. And what was this cutoff? It was the argument that if I take xi to yi, I'm not in A. And if any one of these coordinates happens to be a 1, it doesn't matter what the other ones are, then I take the I coordinate, I take xi to yi. Okay. So this is if any I is equal to 1, then this takes xi to yi by construction. So great. Okay, so now I'm done with proof of my claim. I had codimension at most n. So if I had k of these points, well, like k had to be less than n. That's my definition of codimension. I put a dk in here, and I can't put a dn in there. Maybe this was supposed to be less than. We'll never prove claim 1 because we're almost out of time, but we will prove my proposition. Just enough time to that. At least I gave you a fake proof, so you can go home pretending like you know what's going on. Or you can read the actual proof and you have a heuristic. Okay, so I'm trying to find this x. So I'm going to say let x be maximal. Oh, sorry, let x prime be a maximal subset of that form. X1, xk, y1, yk, as in claim 2. This is x prime. I don't claim it's the x I'm looking for. Okay. Let's do this as two cases. I won't be slick. I'll break it down. Case 1. This guy is the empty set. Okay, what does that mean? That means that I never can find even a point x1 and y1 where x1 doesn't go to y1 by some element of A, right? Okay, so what does that mean? I never have 2 points in different orbits. This means that A acts transitively on my manifold, right? If I didn't act transitively, I'd have some point where you like couldn't take it to the other point by anything in A. Okay, but if you act transitively, then and you contain everyone supported on a little ball, then you contain everyone supported on a ball around each point, because I can conjugate that ball and move it around because my action is transitive. So now by claim 1 plus this implies that A contains everyone supported on, I don't know, union on various balls forming a cover. And our old friend fragmentation says that actually A was the entire group of homeomorphisms. If X is not the empty set, X prime is not the empty set, well, the same logic applies. A acts transitively now on the complement of this finite set, right? Claim 2 tells me that X prime is a finite set bounded by size 2n or something like this. And so what does that mean? That A is, well, it contains the stabilizer of X prime, the setwise stabilizer of the identity component of the setwise stabilizer of this X prime. There's a step to get there that I am getting out of time, using the fact also that A is a closed subgroup. Okay, and so what does that mean, right? Is that like M minus X prime is contained in a single orbit of A. Right? And how do I want to phrase this succinctly to and maybe I want to say so in other words, M minus X prime is contained in a single A orbit, let's say O, right? And O is equal to M minus, I don't know, X for some X, possibly a subset of X prime. So if you imagine in my Torre situation, the original points X were the points that were stabilized. If we knew this was true and we were trying to back solve, right? I wanted to find a maximal collection of these points. I would take all the points in X, and for each one, I would choose one that was outside of X because you could never get there in the stabilizer of X. Right? This is recovering that. I mean, I don't know exactly that that's what happened, but this is what happens in the end. I act transitively on the complement of this bigger set. And so inside of there's a smaller set on which I stabilize setwise. And we already got the desired bound on a codimension that I think we want. Okay. All right. I promised not to go over time, and I at least outlined all the steps. So I'm going to quibble on ahead and answer questions as much as you want. Thanks very much.
Other questions?
So the identity component is just the pointwise stabilizer.
No, imagine I had a single point, and you do what Sebastian was doing in his talk, like I'm on a surface, and I push this point around until I get back to itself, right? Within the stabilizer of that point, the thing I did could not be connected to the identity. If I require you to never move that point, you can't have done this thing that did a point push thing twist type of thing to get around. So that element is in the pointwise stabilizer, but not the identity component of the stabilizer. The identity component of the stabilizer is strictly smaller. No point push is allowed. Okay, but all you can do, but the difference between what you suggested, the pointwise stabilizer, and what I was saying, no point push is allowed, literally is only analogs of point push maps in higher dimensions.
Well, if not, we can
Great.
get you there.
Thanks. If you're only here for the week and you're like me and you have some office